Welcome to The Explainer. Today we're diving into a really cool question. Why does time sometimes feel like it's stretching out? And here's the kicker, why in a very real way it actually is. You know that feeling, right? Maybe you were in a car that started to skid, or you tripped and had a sudden fall. For just a split second, it feels like the entire world just shifted into slow motion. I mean, that quote just captures it perfectly. It's such a common human experience. But what is really going on? Is this just a weird trick our brain is playing on us? Or is there something more happening, something fundamental about the universe? Okay, so here's our game plan. We're going to start with that slow motion feeling and dig into whether it's all just a trick of your memory. Then, we're going to totally switch gears into the hard physics with Einstein's incredible idea of time dilation. We'll look at real-world proof, stuff like atomic clocks on airplanes, and the GPS that's probably in your pocket right now. And finally, we'll bring it all together and look at these two very different kinds of time. All right, let's get right into it. When you have one of those heart-stopping moments and time seems to crawl, is your brain actually processing the world faster? Or is it something else, like a phantom feeling created by your memory after it's all over? So this is where a really fascinating scientific debate comes in. One camp says it's all about memory. The idea is that in a super emotional, high-stakes moment, your brain is just recording way more detail than usual. So later, when you play that memory back, it feels like it lasted longer. The other theory? It says no, it's not a memory trick, it's happening in real time. Your brain's cognitive functions actually kick into overdrive, making the rest of the world seem to slow down by comparison. So to test that faster perception idea, some scientists came up with a pretty wild and, honestly, a pretty terrifying experiment. First, on the ground, they figured out the absolute limit of a person's ability to see flickering numbers on a screen. Then, they had those same people do a 31-meter free fall, we're talking a straight drop, while trying to read numbers that were flickering even faster. The logic was simple, right? If you're really seeing the world in slow motion, you should be able to see things that are normally just a blur. So, what happens when they fell? Well, the results were really, really clear. You can see it on the chart. Based on how much people felt time slowed down, they should have gotten almost 80% of the numbers right. But in reality, their accuracy was basically the same as it was on solid ground. It was a total bust. This was a huge point for the "it's a memory illusion" theory. Our eyes just don't get superpowers when we're scared. But hold on, not everyone was convinced. Other scientists argued that the experiment missed the real point. It's not about your eyes getting faster, it's about your thoughts getting faster. The argument is that your fight-or-flight response floods your brain with chemicals that accelerate your high-level thinking, your attention, your decision-making, so you aren't seeing more frames per second of the world, but your brain has more time to think about each frame it gets. So yeah, the jury is still out on exactly what our brain is doing, but for a moment, let's just put psychology aside, because here's the truly mind-bending part. What if I told you that in the physical world, time actually can and does slow down? This isn't a feeling, it's not a trick of the mind, it's a fundamental feature of our universe. And to understand this, well, we have to turn to one of the most brilliant minds in history, Albert Einstein, and his world-changing theories of relativity. The key concept we need to grasp is called time dilation. And what it means, in a nutshell, is that time is not absolute. It's not some universal clock in the sky ticking at the same rate for everyone everywhere. Your clock can literally tick slower or faster than my clock. Now, Einstein's theories give us two big reasons why this happens. First, there's speed. The faster you travel through space, the slower you travel through time. A clock on a speeding rocket will actually tick slower than one sitting still here on Earth. The second reason is gravity. The stronger the gravitational pull, the more it warps space and time, causing time itself to flow more slowly. This all sounds like science fiction, I know, but it's not just a theory. It was actually proven with incredible precision way back in 1971 using nothing more than a few commercial jets and some incredibly accurate clocks. The experiment was so clever in its simplicity, they took a few atomic clocks. These things are accurate to within a second over millions of years. Synchronized them, left one on the ground as a reference, and then flew the others on airplanes all the way around the world, once going eastward with the Earth's spin and once going westward against it. And the results? Well, they were just stunning. They matched Einstein's predictions almost perfectly. Look at this table.
The clock flying eastward, moving faster with the Earth's rotation, came back having measured less time. It literally lost 59 nanoseconds compared to the clock on the ground. And the westward clock, moving slower against the rotation, came back having measured more time. It gained 273 nanoseconds. The numbers were undeniable. Time itself had physically passed at different rates for each of these clocks. Now, you might be thinking, okay, nanoseconds on a plane, that's a cool curiosity. But this isn't just some weird cosmic trivia. You actually rely on this effect every single day. In fact, without it, your phone's GPS would be totally useless. Get this. Every single day, the atomic clock on board every single GPS satellite gets ahead of the clocks down here on Earth by about 38,000 nanoseconds. Now, 38 microseconds doesn't sound like a lot, but for a system that pinpoints your location using signals traveling at the speed of light, it's a colossal error.
So why does this happen? It's a cosmic tug of war between the two effects of relativity. Because the satellites are far away from Earth, they're in weaker gravity, which makes their clocks run faster. But at the same time, they're zipping around the planet at 14,000 kilometers per hour, which makes their clocks run slower. When you do the math, the gravity effect wins, and the net result is that they run fast. Engineers have to constantly correct for this. If they didn't, your GPS would be off by several kilometers within a single day.
Okay, let's step back and put all these pieces together. We've seen that there are two very different but equally real ways that time can slow down. On the one hand, you have subjective time. This is the time in your head. It's a product of biology and psychology. It's an experience, and it can feel like it stretches and shrinks depending on your emotions. Then, on the other hand, you have physical time. This is a fundamental dimension of the universe itself. It's a measurement, and it physically, measurably changes based on gravity and speed. So this leaves us with a really fascinating thought. We measure our lives by the clock on the wall, the steady physical ticking of the universe. But we experience our lives through the clock in our heads, those moments of fear or joy or boredom. So which one really defines your life? The physical constant measurement or the elastic, unforgettable experience?